Hello everyone, my name is Bingbing. I'm now a lecturer from the Northwestern Polytechnical University in China. It's my honor to have the chance to attend the EAI IoT Care 2021. Today, by taking the opportunity of this conference, I will introduce our recent research, and its topic is robust unscented Kalman filter for target tracking based on Mahalanobis distance. So today, I will introduce my outlines for background, research method, and performance evaluation. The first part is to introduce research background and the significance of our work. So, target tracking technology has received an extensive application for military and civil fields. However, it is constantly developing and updating in order to achieve the accurate tracking with increasingly complex environments. Therefore, accurate target tracking problem has become the current research hotspot. Filtering technology is a key for the target tracking. Kalman filter is extensively applied in target tracking. It can obtain the optimal state estimation under the principle of the minimal mean square error for a linear Gaussian system. However, KF is poor to deal with the nonlinear problem in radar target tracking system. In the field of the target tracking, there are two commonly used methods to solve the above problem. One is extensive Kalman filter, which can transfer the nonlinear filter problem into a linear one by using the model linearization. But its accuracy is poor when the system is highly nonlinear and needs compute complex Jacobian matrix. The other one is the Unscented Kalman filter, which can achieve higher approximation accuracy than EKF. However, UKF has poor robustness against the abnormal observations. The estimation accuracy of the filter will be deteriorated when the reader is subject to abnormal interference or equipment failure. In the second part, the robust UKF is proposed and introduced on the basis of Mahalanobis distance for enhancing the robust performance of a radar single target tracking system against the abnormal observation information. This method firstly used the concept of Mahalanobis distance to identify the abnormal observation involved in the radar tracking. And then a scaling factor with robust property is determined and used into the innovation covariance of classical UKF to weaken the negative effect of the aberrant observations on system estimation. First, we established the system model for radar target tracking. It is divided into state model and observation model. It is assumed that the target P moved at approximately a constant velocity in horizontal and vertical directions. Thus, the system state variable and the state model of the target motion in Cartesian coordinate system is described by the left hand. And since the slant range and the azimuth of the target is measured by radar, the observation model can be established by the right hand. Then we developed a novel way of aberrant observation identification by utilizing the theory of Mahalanobis distance. Based on the definition of Mahalanobis distance, we define the innovation and its covariance of filter and construct the square of Mahalanobis distance of innovation vector. Then, from the statistic knowledge, the square of Mahalanobis distance of innovation vectors obey a chi-square distribution. Finally, by using the theory of chi-square hypothesis testing, the criteria can be constructed to identify the aberrant observation of the system. After completing aberrant observation definition of the system model, a robust UKF is proposed on the basis of Mahalanobis distance in the following of resist the aberrant observation for improving the robustness of tracking system. Its key is how they determine the robust factor. Thus, let's focus on the part. It firstly modified the innovation covariance by introducing a robust factor, then constructed a nonlinear equation through the concept of Mahalanobis distance, and the Newton iterative method is used to solve the above nonlinear equations. By the iterative solution, the last iteratively result is the determined robust factor. The calculation process of the proposed robust UKF can be summarized as the following and described as this flowchart. If the Mahalanobis distance criterion is not satisfied, the classical UKF will be performed to achieve the system state estimation. Else, the robust factor will be iteratively solved to update the innovation covariance for renewally the system state estimation. In the third part, the proposed RUKF is applied to radar target tracking system, and as a result of Monte Carlo simulation are compared with the existing method. In the simulation time is 1,000 seconds, and the Monte Carlo run is 10, and the measurement noise covariance is shown in the right hand. We try to evaluate the proposed method when there are existing abnormal observations, and supposed that the observation noise covariance suddenly increasing to 50 times of its real value in 400 seconds to 600 seconds. This figure shows that target position and velocity error of the x-axis and the y-axis. Calculated from the above that 3 method. It can be seen that from 0 second to 400 seconds and 600 to 1000 seconds, since the abnormal observation is not introduced into the target tracking system, the above 3 algorithms all can quickly and accurately estimate the target's position and its velocity. And its tracking precision is very close. However, during the time of 400 seconds to 600 seconds, the classical UKF and existing RUKF's estimation precision is obviously decreased because of the aberrant observation for the target tracking system, while the proposed method is significantly have a more accurate estimation for the radar target tracking system by embedding a robust factor to regulate the filter gain. Its estimation error is significantly smaller than both the mentioned classical UKF and existing RUKF. Different from the existing RUKF, the robust factor in the proposed method is directly derived from the concept of Mahalanobis distance, which is not determined by artificial experience. Thus, it has better regulation effect. And this gives the intuitive comparison of the position and the velocity's average absolute error for the target in x-axis and y-axis directions. Achieved from the above 3 methods during the 400 second to 600 second, the other time interval respectively. Further, the maximum velocity and position errors derived from the classical UKF, RUKF, and MRUKF during the 400 second to 600 seconds are also calculated and intuitively compared. The above simulation results show that when the radar target tracking system involving abnormal observations, the estimation accuracy of the proposed method is better than the mentioned classical UKF and the rest of the method. At the same time, it significantly enhanced the robustness of filter, thus improving the target tracking performance of the radar. Finally, thank you for listening.